So, we have discussed about Auger electron spectroscopy in the last class, and this is the continuation of that lecture, and I have basically talked about the basic principles of Auger spectroscopy, the applications where it can be used, and I have given you some basic equations and diagrams to explain how the Auger electrons are generated. Now, in the subsequent lecture as of today, we are going to see different applications of Auger electron spectroscopy, and finally I am going to show you the actual machine or actually configuration of a machine in the Auger spectroscopy. So, before that, let me just reiterate the following thing, which I should do it very carefully. The reason Auger is very famous and very useful technique is because the signals which we get from the samples are basically from a very small thickness, very small thickness of the surface. This is what is shown here. If you look at the sample surface, and then there are different kinds of signals which are generated because of the inherent excitement or excitation by the primary electrons. As the primary electron falls on the samples, it causes a lot of excitation, and that leads to different kinds of signals. Signals can be backscatter electrons, signals can be secondary electrons, or even characteristic X-rays which are used in the scanning electron microscopes, and also we will have Auger electrons. But if you look at the interaction volumes from which the signals generate or get generated, it varies from very large thickness to a very small thickness depending on the type of signal. So, for the characteristic X-rays, the interaction volume actually is very large. The depth from which the information can come is of the order of less than 3 micron, 1 to 3 micron actually. On the other hand, the backscatter electron comes about, you see here, backscatter electron comes about approximately about 2 micron. Secondary electrons comes from about approximately about couple of hundreds of Armstrong. It's hundreds of actually nanometers, not Armstrong. But Auger, which is very significant in radiation, comes from only 4 to 50 Armstrong depth, and it is only possible to get Auger excitation for atomic numbers higher than 3. So, you can always get excitation from electrons from elements which are having atomic number more than 3, that is higher than the lithium. So, that means the information which is coming from Auger is basically coming from a very small depth on the sample surface, and that is why it is very significant tool to analyze those kind of small features on the sample surface in the Auger. So, this is what is shown here. This is the electron beam, you can see here, and then this is the depth from which the information comes in the Auger. Depending on the spot size also, and not only spot size, electron gun, the spatial resolution means this way resolution, spatial means this, not the depth but the XY would depend on. In the direction perpendicular surface analysis, volume depends on the electron mean free path. That is what I am shown. Mean free path is high, then electrons can generate more Auger. It is low, then so mean free path is shown here as a function of electron voltage, electron energy actually. If you see here, gold and this is silver, they have a very small mean free path. Mean free path increases to like molybdenum, cerium, beryllium. Okay, so that means, or even some other elements like phosphorus. So, that means the mean free path actually depends on electron excitation energy is very high for the gold, silver, others, but very low for the beryllium and other and the phosphorus and iron also. So, that actually tells us that perpendicular depth will also vary depending on the mean free path of the electron and different elements. This also sets that what kind of elements you can analyze from a particular depth. Well, now let us move into the applications. As I said, we are going to discuss today that the the analysis depth was just the information I wanted to convey clearly. We have already discussed about the chemical analysis by using XPS or X-ray photoresist spectroscopy. AE is one of the best complementary techniques for XPS in the chemical analysis. Depending on the kinetic energy of the auxiliary electrons, AES is more sensitive to surface than the XPS. Heat also gives us chemical shifts depending on the characteristics or the basically ionic state of the element present. Auxiliary landscapes can be used to determine the chemical state of a given element in a sample, and in studies the charge transfer in alloys. This is very important. One can actually study the charge transfer in alloys. Let us now look at the differences in the line shape and the peak positions for the carbon auxiliary spectra, K, VB, VB stands for vacuum, in different CX and HY compounds. First let us talk about acetylene C2H2. There are triple bonds between two carbon atoms. You can clearly see there are three distinct peaks, one broad and two very sharp peaks coming at around from about 240 to 260, 255 actually kV. But if you go to C2H4, that is ethylene, where there is a double bond, you can clearly see the peak splits 1, 2, 3, 4, 5, 6. Not only that, the positions of the peaks also little bit has shifted to the left side, that is lower kinetic energies. Now if I go to the element, the CH4, that is the methane, I can clearly see one big strong peak clearly visible and others very small peaks are visible. So that means the electron yield versus kinetic energy diagram can distinctly differentiate between carbon compounds from ethylene, from acetylene to ethylene to methane. This is just basically to detect a particular compound. We can use these signatures to detect whether they are present in the sample or not. That is the first thing you must know. So that means chemical analysis means qualitative and quantitative analysis. Qualitative analysis means whether we are able to detect a particular compound or element or particular species on the sample surface or not, and second thing, if we are able to detect many chemical species, whether we can quantify the amount of each of these elemental species or compounds present in the sample surface. This is very typical of any spectroscopy, but auxiliary also gives us much extra information other than this only. Well, now let us talk about little bit about the elemental shapes for the different first transition metal series, scandium, titanium. Scandium stands for 21 and then zinc stands for actually 30. So if you go from 21 to 30, 2p 3 by 2 peaks actually shifts 399 electron volts to 1022 electron volts. 3p peak shifts from 29 to 89. Now if you make alloys between them, actually suppose if you make alloys between scandium and titanium, there will be shift of 327. Similarly between titanium and there will be shift of 421. So you can clearly see the shifts because of the formation of alloys among the different elements. This alloys means solution types. Well, not only that, one can actually look at the chemical shifts in terms of atomic number versus electron energy diagram. This one I have already shown to you. Now if you carefully look at this diagram, it says different transitions like KLL transition, LMM transition, MNN transitions and higher depend on the atomic number. So obviously if the atomic number is less than about say 16, that is for sulfur, you will not have any, you will have only KL transitions. Only when atomic numbers of the elements higher than 16 and lower than about 45, you have basically LMM transitions. And there is a small overlap obviously between LMM and the KL transitions. Similarly, there is a small overlap between MNN and LMM transitions also, but MNN transitions actually occurs mostly for the elements with a very high atomic number like more than 45 and less than about 84, 83. So that means depending on this from this diagram actually one can actually understand that if I have alloys, suppose if I have alloys between aluminum and the niobium, obviously there will be chemical shift of the peaks from both aluminum and niobium because of these different transitions. Not only that, there will be also chemical shift if you consider only suppose elements which are very close by, suppose if we consider boron and aluminum. So there will be some chemical shift possible even in KLL transitions because of the atomic configuration, electron configuration change or charge transfer issues in the alloys. To give you much better perspective how the chemical shift actually is observed in the OGR, I am not actually discussing the exact physics behind the chemical shift because this is what I have done in XPS. The theory is same whether it is for XPS or OGR. Only thing which I am describing here is that how this chemical shifts can be used to detect a particular type of chemical bonding or particular type of electronic configuration. Let us consider silicon and oxidized silicon. In silicon you have silicon bonds, and if I take OGS spectra, the silicon bond gives us a very characteristic peaks at about 1617 to 18 electron volt. But when the silicon is oxidized, which is most of the cases happens on the surface of the silicon, you have a silicon oxygen bond. So therefore, because of the presence of silicon oxygen bond, the peak from this one gets shifted to the lower value, and it has been observed the peak comes at about 1605 electron volts. So OGS spectrum or spectra from the elemental silicon, which is very pure, and the oxidized silicon, which is having oxygen as one of the element present in the along the silicon, can distinguish the type of bonding between these two very clearly. And it is even much clearer in OGR than in XPS that this kind of chemical shifts are actually observed and can be used to differentiate between the different kinds of bondings, bonding in the sense of whether it is a bond between similar atoms or dissimilar atoms, oxidized, nitrides, all can be detected there. To give you much much better perspective in the sense, let us now talk about elemental germanium and germanium with a thin oxide layer, same as silicon, but here the elemental germanium is a germanium single crystals. So you have germanium 0 peak, germanium 4 peak, you can see this is germanium LNM transitions. On the other hand, if you look at if there is oxide, that is how they basically these two. This is actually from the pure germanium, this is from the oxidized peak. So this is oxide, this is pure germanium. So you have an oxide layer, there is a shift from the pure germanium 0 and germanium 4 peaks to the lower level, say from 1175 to 1145 germanium 0 peak shifts. Not only that, even the OGR is very sensitive to presence of very small quantity element like semiconductor doping. Let us talk about semiconductor doping of a silicon. The difference between P and N type silicon can also be distinguishedly seen in the OGR spectra. That is what is shown in this slide. So you know that P and N type silicons can be created by doping different elements. If you dope with P the 5 like phosphorus with silicon, you get N type, and if you dope with boron you get P type or other elements like. So this is the yield in the XPS and kinetic energy plot. You can see N type and P type, that is a distinct position of the peaks, and the energy difference between these two peaks are about 0.6 electron volts. So that means XPS is so sensitive, it can also detect this much of energy spread when you dope the silicon to make it N or P type. The small shift is sufficient enough to tell us, let us know that it is indeed a n type or p type. Well, one can actually detect even this peak shift. This picture is not very clear, I have taken from a book, but it is not clear, but still I want to show you because so that you can get idea. So this is basically difference between n and p type. This is n type, this is p type silicon in the image. So we can actually take a silicon single crystal and dope elements of different types and make a NPN junction, or PN junction basically here, N and P, this is the junction. So you can see that peak shift changes, peak shift as a distance is basically changes continuously from N type to P type. This is basically the quantified value of the peak shift from N type region to P type region. So one can actually get an idea of continuous change in the doping characteristics as a function of distance by taking XPS spectra at different points on the sample surface like this. This is possible. There are major applications. Next thing which I would like to discuss is the quantification in XAES. I think I have discussed a lot about quantification in XPS. Similarly, RGS spectra can also be used to quantify different elements. So quantification analysis using first principle is possible, but normally not done due to large difference between coupling schemes that govern the RGS transitions in a multi-ionized atom. What it means is that if there is a multi-ionized atom, then there will be large differences between the couplings of different transitions, and this makes the quantification difficult. The most common analysis use sensitive factors derived from the pure materials or standards. These materials also have a lot of problem of precision and should be used judiciously. Because I like you to know that AES allows us to quantify different elements present on the sample surface, but precisions are much poorer than XPS. So what is the actual mathematical equation which uses sensitivity factor? Actually RGS electron density in any position XYZ is given by this big equation. This is the incident beam intensity, this is the cross section, this is the energy level, this is the diameter from which it is coming, is also a function of energy level and the incident beam angle, and these are all, this is the atomic number of atoms which has undergone transitions, exponential, transition wavelengths, and cos theta is scattering. This is very complex formula and I do not want to discuss in detail because that requires a lot of theories to be first discussed. Simplified formula for homogeneous material is that Xi, the amount of particular element I present, is given by Is by Si divided by summation of Ij by Sj, where J can be summed over. So therefore Is is basically the scattering factor and I is the intensity. So if I know the scattering factors of the elements present and if I know the intensities of the each peaks, I can actually indirectly calculate what is the amount of present in the particular specimen. So let us go back to the RGS spectra. This is RGS spectra coming from oxygen, iron, nickel, and obviously carbon is inevitably present or omnipresent in any sample. So a small carbon peak which is sometimes used to even calibrate. So if oxygen KLL transition here, then iron LMM transition here, and nickel there is a small peak here and these two peaks basically LMM transition of nickel. Now as you see here, the big peaks are this one for oxygen, this one for iron, and this one for nickel, correct. Now I can actually calculate the area under these three peaks and get the intensity, right. So and then if I know the scattering factor, I can calculate or quantify each of these element presence. One can actually take basically differentiate these intensity with respect to energy, then can get much better plot which I have discussed already about the RGS spectra. Oxygen spectra becomes like this, nickel comes like that. So this way one can actually improve the quantification precision much better way. Well, let us now look into much detail. This is the sensitivity factor with versus atomic number. Sensitivity factor is what I discussed. This is a sensitivity factor, as you see, from this part to this part. It contains the transitions energy level, the scattering cross sections, incident beam energy level. So sensitivity factors can vary from 10 to the minus 2 to 10 depending on the atomic number and depending on the transitions. For a 3 kilovolt primary electron beam, this is calculated. For KLL transition, sensitivity factor will be very much lower, and it basically close to 1 for most of the elements you studied. This is very important because KLL transitions is normally seen for all the elements less than atomic number less than 16, or which are lower actually than sulfur, and so therefore this is what we get, and the sensitivity factor is low. That means the quantification done from these elements by AES is even much less precise. The highest sensitivity factor is obtained for LMM transitions, and LMM transition actually takes place for a large number of elements starting from atomic number 16 to atomic number about 65. Let me just go back there and to show you what is that. So this is this is 45. So this basically starts from 12 to 45. So that's a large range. That is the range we are having a very large value. So you can see here this is something like 12. This is what something like 35 or 40 here. So in this range from this to this actually the sensitivity factor is quite high. So therefore our measurements will be better. NN transitions actually occurs at large atomic numbers more than 40 and about to 85, and this is also very high for a atomic number ranges from 38 to 62. So that means from all the atomic elements with atomic number from about 16 to about 62, the sensitivity factor is quite good, and actually it is higher than 0.5. So that means we can actually use AGS for these elements to get much better quantification analysis. Well, this also depends on the primary beam. As you know, if I use a 10 electron primary beam, this is how the curves get shifted. Well, not much shifting has happened except for the we are getting an extra transition at LLMM transitions, but LMM transitions actually we are getting actually extended LMM transitions, you can see there. So little bit of change happens, but not much. Now we can actually do it. This is the sensitivity factor, so we can actually do it much better way, that by assuming the concentration to be relative ratio of atoms, we can neglect the terms that depends on the instruments. So we get this is AI, sigma I. I think there is no need of discussing, we have already discussed about that, but this is a different scheme. The important thing is you have to understand it is a semi-quantitative technique, it is not a quantitative technique per se like XPS. Well, to determine the peak intensity, I know that is what is very important because you want to calculate the area under the peak to know the actual intensity. So one has to be very careful about to measure the peak intensity. I am showing you some plots to make you understand how that judgment is very important. So this is the kinetic energy, this is the CPS. As you see, this is the plot of silicon. The P and B is basically the peak and the background. So you have to consider the peak area this way. On the other hand, if you take dNE by dE versus kinetic energy, you get a much better peak. This is your peak area, correct? So that means it is better to use dNE by d than NE by E versus kinetic energy plot to determine the area under the peaks, so that quantification is much precise. Well, to give you a analysis as compared to the others, for compounds, nitrogen compounds like this, chromium nitride, vanadium nitride, titanium nitride, scandium nitrides, the fast low transition metal nitrides, you have basically L3M2 or 3M2 peaks for this, You can see these are the peak positions, the changes, and for L3M2MT the peak positions actually are then this is what is important in as deposited condition. This is how the intensity ratios varies, 1 B stands for for these ones, this is the severe overlap, so we cannot detect, B means we cannot detect, that is overlap. These are the ratios. After ion bombardment, ratio gets modified, right. On the other hand, if you do using RBS, that is what we will discuss in the next. The RBS means other purpose backscattering, which is the SIMS tool, the secondary ion mass spectroscopy. This is the data we get. So you can see this is very close for the vanadium scandium nitride, okay, but this is not. This is close to vanadium nitride. This is little bit lower the actual value. So that means AES is not that great analysis as far as the SIMS or XPS is concerned. Second important observation from this is that if you do the bombardment, after bombardment and before bombardment, there is a change in the nitrogen to metal peak ratio. This is the nitrogen to metal peak ratio, I gamma by I alpha. This peak ratio actually decreases after sputtering. That is what you see here, from 2 it becomes 1.82, 2.5 to become 2.1, 1.4 to become 1.01, 1.3 become 0.94. That is clear, that is because nitrogen actually gets removed during sputtering, because there is a light element. So many times sputtering is bad. That is why it is better to do this analysis in the vacuum without any sputtering. Next thing, so after giving you an idea of chemical shift, chemical detection of different elements or different species as well as quantification, let us go to depth profiling, Auger depth profiling. Well, what is Auger depth profiling actually? As you know, you have this is a sample suppose, and you have incident electron beam coming into picture, and then it generates Auger electrons, it goes to the electron energy analyzer, and then you get the peaks. Many times actually you can routinely get these peaks. Now we can actually use argon ions to sputter the sample surface sequentially. That means if I have a sample initially like this is taken from this website anyway, then I take information at the beginning from this much area, get the Auger spectra, then using argon ion I remove small thickness, very small thickness, sputter out of the order of 10 to 20 Armstrong, and then again collect the Auger spectrum. That is how I keep on doing it. So that means slowly I increase the depth, or slowly I increase the depth of sputtering and collect the Auger spectrum. And if you do that, then one can actually do the profiling. That means one can actually determine the elements present at each depth and also quantify different elements present. So this is one plot which is showing here, this is sputtering time versus intensity. As you see here, you have a aluminum concentration, gold constant decreases, aluminum constant increases, oxygen constant increases, titanium. So you have chromium, titanium, gold, aluminum, oxygen. Okay, this is basically a gold layer on the top, you have aluminum oxide at the bottom, and then you have a interlayer between this gold and this aluminum oxide. The interlayer consists of chromium and titanium, and that is what you see in the this concentration of the chromium titanium is very high in the intermediate zone. Gold concentration was high at the beginning, that is from 0 to about 20 minutes you have a large gold concentration, then it decreases, and finally once you reach the aluminum layer, aluminum oxide layer, you have aluminum and oxygen. So what does it mean? This is a very important aspect which you must know. This is actually required in material science. That means that this is although this very sensitive technique, this can be used to even do such a fine scale depth profiling by using argon ion sputtering. Well, it looks very simple and very genuine and very interesting method, but it has a lot of problems. It can lead to different artifacts. What? It can lead to sample charging because of the sputtering. It can lead to topographical feature resulting from non-uniform sputtering of sample. It can lead to even preferential sputtering, depends on the element present. Some elements will sputter easily, some elements sputter less easily. Then there are beam effects like argon ion beams, and it can also lead to, most notably, ion beam mixing, because you are putting argon ions that can lead to mixing of two different elements or two different species, and that can modify the results. So one must remember these are the problems in RGS depth profiling. Otherwise, this is a very nice technique. Well, this is not clear to you visible, but just to show you that AFM actually leads to very small thickness on the top surface. RGR is approximately 100 micron. So RGR, this is RGR, AES, it's about 100 micron depth analysis can be done. Others like XPS can go up to very high, RBS can go up to even a couple of thousands of Armstrong, and FTR things can go up to even micron level, which I will discuss in detail when I compare these different techniques. So to give you much better idea, this is another example, sputtering and non-sputtering, copper and nickel aluminum alloys presents, and as you see here, copper and nickel alloy, actually not aluminum, copper and nickel alloys. As you see here, this is the depth profiling of the passivated layer. This is the clean sample. The clean sample is giving much better results, signals, than the passivated. Passivated means it might have got oxidized surface layer. So RGS sputtering profiles for the copper nickel alloys is basically taken from McCurry et al. It tells us that it is always better to clean the sample surface by sputtering and before taking even the profiles. Another example, this is a gallium nitride substrate with a PD interlayer, and there is a aluminum layer. This is 200 Armstrong PD layer and 1100 Armstrong aluminum layer. This is basically a multi-layer as grown. Now one can actually do this schematic profile or profile and then profile. This is the aluminum depth, PD depth, and gallium nickel. You can see the quality of data one can get, very good quality data one can get using this. This is another example. I think this is PD, germanium, oxygen, aluminum, many things are present. This is sputter time versus atomic concentration. This is aluminum, this is oxygen, this is PD, this is gallium, this is nitrogen. One can carefully do that. Same sample actually. And then if you annihilate, it gets changed. I can see that the oxygen actually profile has remained same. Palladium profile has got changed because palladium has moved into inside the aluminum, and on the other hand, nickel gallium remains same. So one can actually do this kind of analysis also in the actual sense. The last technique which is useful, which I am going to discuss, is the scanning RGR electron microscope actually, or inlet spectroscope. You can actually scan the surface and do that. What you do is basically you can use the same technology as used in the SCM, and your beam which is coming and electron which is coming and following the sample surface can be allowed to raster on the sample surface, or can be allowed to basically scan the sample surface. So as you scan the sample surface, you can actually gather information from each point on the sample surface due to interaction of the electron beams with the sample surface, and then generate an image. Instead of depth profiling, you can generate actually an image. So details is shown here. What you see here, this is scanning coil, this is the electron beam filaments, this is the objective lens, so this is the condensation lens. So if a scanning coil, it will scan the beam. Scanning coil is nothing but basically same as an electron scanning electron microscope. Then you have a secondary electron detector here. This is ion detector net here, which is sputter the sample carousel. So and the actual picture is shown here. This is taken from University Illinois. They have a facility like this. So what is done here? Let me describe in a schematic diagram. This is the electron beam falling on the sample surface. So you are basically generating KE1, KE3, KE2 different kinds of transitions of energies, electron with different energies. This can be detected because of the presence of different elements actually when you scan, and then you can image. This image actually is I do not know, this is the blue is basically titanium. This is taken from this website, not from my work, so there are pictures. The sulfur is basically the green is basically for sulfur, and red is basically for silicon. As you can see, this is the cross sectional conventional SEM image, which does not give much data. It only shows there are different areas, sample surface, red and the black. This has been basically made color. I think this is sulfur backscatter image, yeah, sulfur backscatter image. So this is basically sulfur regions. So as you can see here, sulfur is green, and in the AES SAM or the scanning or RGS microscopy, you can see these red regions are basically coming from silicon. These are all silicon, okay. These three regions, silicon, 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 and then you have sulfur and the titanium sitting. So the blue here, this much smaller is blue, and this is green. Sorry, blue here is basically titanium, green is basically for sulfur. So scanning electron microscope shows a large area of sulfur. RGS microscopy shows there is a thin region of sulfur between silicon and the titanium. That is the difference actually one can clearly see when you use scanning RGS microscopy, which is much more sensitive than the EDS analysis, electron energy density spectroscopy analysis in the scanning electron microscope. Well, last thing which I am going to discuss is the RGS setup, or how the RGS electron spectroscopy is done. Yes. So as you see here, the schematic diagram here, which is quite complex. This is basically 4 grid LED optics setup, which is used to detect data. This is a sample, and this is the electron gun. So electron comes from the gun and from the sample, and then you have basically secondary electrons generated, RGS electrons generated. So one needs to detect them, and that is why 4 grid LED optics is used. This signal, this one is fed to a pre-amplifier, then there is a phase shifter, then there is a lock amplifier, and then it goes through different kinds of things. Finally you just detect the signal in a computer. These are basically electronics used to modify, not to modify, to actually improve the signal to noise ratio. And this is the geometry, that means basically it's a kind of a hemispherical geometry is used to detect all the RGS electrons present. Remember, we cannot actually throw out fully the secondary electrons, and that remains in the RGS spectroscopy always. So this cylindrical mirror analyzer is basically uses the same thing. This is the electron gun. So it falls on a sample. The sample actually electron gun for samples, and you apply pass energy, and then you can actually remove the secondary electrons to that. So when energy resolution scale up to EP, and then you have a coaxial design. Coaxial design like this, you can actually eliminate shadowing effect. You can have better transmission, relative short distance. Normally lock-in interpolars get differential distribution very deeply, that is the dNE by D. That is what I plot, dNE by D versus E is plotted in RGS. So this is why you need to use lock-in amplifiers. You can always use hemispherical analyzer, that is what I have discussed at the beginning. This is the inner hemispherical energy, and this is the aperture. The sample electron falls, and then it falls, goes through this hemispherical detector and detected. Well, I think that's all. Rest of the things cannot, this will be, if I get time, we'll discuss. Otherwise, next lecture I am going to start the secondary ion mass spectroscopy, which is the last surface spectroscopic, advanced surface spectroscopy technique in this course, and then I am going to compare these 3 techniques and wind up this particular portion of the syllabus.